All right. I just defined scalar quantities. We say they are quantities that have magnitude, but they do not have direction. When we talk about magnitudes, when we talk about magnitude, other terms we can use to refer to magnitude include size, value, length. Are you following? Modulus. These are various terms that we use to. I'm trying to check what is happening with respect to network. I think we can kick off. I've tried boosting the network. It's not easy. It's not easy, Quite a tough one, the way network challenges us. All right. Let us move on. So I just give examples of scalar quantities. Okay. Now, it's important for you to know that when you talk about scalars, they are also simply numbers. They are also simply what? Numbers. So if I give you something like temperature of 20 Kelvin, so that number, the Kelvin is just the unit, okay? So the 20 is sufficient to tell us what we are talking about. I hope you're following right. Now I can talk about a distance of 50 meters without specifying the direction that something is taking. Because once I specify the direction, I'm no longer talking about distance. There, displacement will not come in. And hence, we would no longer be talking about scalar quantities, okay? So, distance, I can just quote a number and the unit, and it is sufficient. All right, let us move on to the concept of the arithmetics of scalars is very simple. Scalars can be added, they can be subtracted. Okay, you can multiply scalars. You can also divide a scalar by another scalar. Is that okay? So the four basic arithmetics in mathematics can be carried out on scalar. You can add, you can subtract, you can multiply, you can divide scalars. Now let us move on to vectors. As a matter of fact, when you talk about scalar quantities and vector quantities, much about this topic, all right, is based on vectors. So once again, I want to say welcome to the class as we now look at the main part of this topic, vectors. What are quantities known as vectors? Quantities that are called vector quantities, what are they? So, if you know the definition of scalar quantities, you can use that idea to also define vector quantities. Okay? Yeah. So, we define vector quantities as quantities that have both magnitude and direction. Quantities that have what? Both magnitude and direction. So, they have size, they have value, they have modulus. Are you following right? Good. And they also have added to their magnitude the direction. So here I'm going to write magnitude, yes. Vector quantities, they have magnitude. Direction, yes. Vector quantities, they have direction. So you see clearly the difference between scalar quantities and vector quantities. Why scalar quantities have only magnitude? Vector quantities have both magnitude and what? Direction. Okay? Now your examiner would like you to know some examples of vector quantities. Okay? Quantities that have magnitude and direction. What are some of the examples? So we can think of the following. Some examples of vector quantities. Vector quantities. You can add up to your own examples, all right? You can browse, you can Google and find out other examples of vectors added to the ones you're going to see here. Velocity, okay, let's start with displacement. Displacement is a vector quantity. Displacement is a vector quantity. Okay, force is a vector quantity. Force is a vector quantity. Velocity is a vector quantity. Acceleration is a vector quantity. Acceleration is a vector quantity. We have other vector quantities to include momentum is a vector quantity. Momentum. Impulse is a vector quantity. Impulse is a vector quantity. Electric field is a vector quantity. Electric field is a vector quantity. Even magnetic field, electric and magnetic field, they are vector quantities, etc. So you can add up to the list of your vector quantities. Okay? When a student is preparing for examination, let's say physics exam, it's important for that student to know how to define scalar quantities. The student should know some examples of scalar quantities, as many as possible anyway. All right? The student is also expected to know the definition of vector quantities and as many examples of vector quantities as possible. Now, before we move on to talk about dimensions of vector quantities, I would like us to give attention to certain rules that can guide us to know quantities that are vectors, especially if we know the formula of that quantity. So I want to expose a secret to you now. Using some formula, okay, to determine quantities that are vectors. And it's important for me to tell you or to state that the approach, the knowledge, the secret I'm about to expose to you makes use of one concept called scalar multiplication of vectors, also known as dot multiplication of vectors. As we move on in this topic, we are going to see that there are two ways you can multiply vectors. But don't worry until we get to that point. We have the dot product method, also called the scalar product of vectors. And then we have the second method of multiplying vectors called the cross product or the vector product of vectors. But like I said, when it is time, we discuss that. Why I just mentioned the two ways or methods of multiplying vectors is because I want to give you some rule of thumbs, mnemonics, tricks, all right, secrets that could help you to know if a quantity is a vector quantity, especially if you know the formula of that quantity. Especially if you do what? Know the formula of that quantity. Some Mahajan, magnitude means value. Yes. The magnitude of something is the value of that thing, is the size of that thing, is the modulus of that thing. That is why I said that scalars are simply numbers also. Scalars are simply what I said, numbers also. So the value of something is actually the magnitude of that thing. Are you getting me? The size of that thing. I hope I've answered your question, Sam Mahajan, all right? Okay, so let us move on. We are going to look at certain rule of thumbs, all right, rule of thumbs that you can use to identify vectors, okay? Now, let's say basic principles, okay, basic principle, basic operation, okay, let me use it as operation, basic operation for identifying vectors, identifying vectors. But take notes, okay, take notes. These principles here that you use to identify vectors to the formula of that quantity. So let me indicate basic operation for identifying vectors when the formula of the quantity is known. When the formula of the quantity is known. Of the quantity is known. Of the quantity is known. Good. So let us look at these basic principles. Like I said, although the principles might be important to guide you, but before you can show you this operation, you must know the formula of that quantity first. So we start with this. Number one, permit me to use V for vector and to use S for scalar. And I would like us to use a rule of thumb still to guide ourselves that vectors should be assigned negative. Vectors should be assigned negative so that scalars will be assigned positive. Okay, I'm just saying this generally, something that would guide you. The reason I am coming up with this principle is there is minus times minus, you see it will change to plus. Okay, if you have plus times minus, you will get minus. All right, so if I say vector V should be minus, let's take it as minus mathematically. And then scalar S, let's take it as plus. Okay, let me indicate all these things on the board as guiding principles, okay? Let me indicate them as guiding principles. Please, I don't know, I think I have to, let me boost the network a bit because it appears the board is a bit blurred. Please be patient a bit. Let me see. Trying to check the network situation. Okay. It's cool. The network is good. All right, let us move on. Let vector be negative and scalar, we're going to use S for scalar, be positive, so that this thing will guide you as I give you some of these rules. Now, number one, if I have vector times, so I'm using dot for the times, dot, vector times vector, vector times vector, it will give you scalar. It is just like you talking about minus times minus in mathematics, that operation. If you multiply negative by negative, you know you're going to get positive. So vector times vector will give you positive scalar. So if you give me a quantity, and it happens that that quantity is obtained from the multiplication of two quantities, which are vectors, we expect that the final result will give you a vector. So the final result rather will give you a scalar. That is, if the multiplication is a dot product. I'll give you a good example, but I'll still wipe it from the board. Look at this quantity called work. Work is force times displacement. Work is force times what? Displacement generally. Okay? Force. Let me write it this way. Force times displacement to give you work. These times you are seeing here in vector multiplication. in vector multiplication, I am saying that work is equal to force times distance. But this times here, in vector multiplication, displacement. Now, force is a vector quantity. Displacement is a vector quantity. You can see them here. Displacement, force. So they are dot product. When you multiply them, if the multiplication is a scalar multiplication, the result you are going to get will be scalar. Vector dot vector. Vector times vector. Take note, the multiplication there is a dot product multiplication. When I treat methods of multiplying vectors, you learn about dot product more. So since I have two vectors multiplying through the dot product method, the result I am going to get, that quantity will be what? Scalar. Vector dot vector, vector times vector, where the multiplication is a dot product. Okay, we give you what? Scalar. In fact, I didn't write work here. You can add it to the list. Work is a scalar quantity. What about this one? This guy, this quantity, power. Power is equal to force times velocity, where the multiplication is a dot multiplication, not cross multiplication, not cross product, a dot product. This quantity power is obtained from multiplying force by velocity. Force is a vector quantity, velocity is a vector quantity, so they are dot products. The quantity it is going to produce will be a scalar. Vector times vector will give you what? Scalar. Just like minus times minus. All right, so you see, minus times minus will give you plus. Like I told you, let's take vector as minus and then scalar as plus. So this principle can guide you. If I give you a particular quantity and you know the formula of that quantity, it can help you to know what that quantity is, if it is scalar or vector. Now, number 2, we give you vector. Vector times scalar will give you vector. It is just like minus times plus will give you what? Minus. You know, it's still the same as scalar times vector will give you a vector. Okay? Then take note of these. We know scalar times scalar will give you scalar. Scalar, if I let me include it. But here I actually mentioned basic operation for identifying vectors. So let me forget about... okay. Let me still add up. Scalar times scalar will give you what? A scalar quantity. Scalar times scalar will give you scalar for you. It will not change to vector. It won't. It won't. Vector times vector change to what? Scalar. But scalar times... All right. Let me adjust the camera a bit so that... Good. So trying to make sure that network is not over disturbing. Please let us move on. We're about 30 minutes into the class now. Of course, as you know, our classes, all right, it's usually 1 hour, 30 minutes class. On Mondays, on Wednesdays, and Fridays, I come on live by 8 o'clock p.m. to hold our online class. Monday, maths. On Monday is mathematics. On Wednesday is chemistry. On Friday is physics. Then, of course, we have practical sections where you just follow up with our classes. You would see the link to guide you to the practical works, chemistry practical and physics practical, but that one is based on pre-recorded video lessons, okay? I'm going to wipe this. So we have been able to cover one important part of scalars and vectors, where you are meant to know the definition of scalars and examples of scalars, definition of vectors and examples of vectors. We shall now move on to the concept of, we're going to move on to a concept of the dimensions of vectors, right? Vectors can exist in how many dimensions? Meanwhile, look at this guy, please. Vector times scalar giving you vector. A good example is having something like force. Force is a vector quantity. Why? You know, the formula of force is equal to mass times acceleration. Mass times what? Acceleration. Okay, good. So acceleration is a vector quantity. Mass is a scalar quantity. So scalar times vector, vector times scalar will give you a vector quantity. Does that make sense, right? To give you a vector quantity. I think I am supposed to talk about that one of division as well too. Okay, if you have vector divided by scalar, you will get vector. So if I give you any formula where a vector is divided by a scalar, you will get what? Vector. Take note of that. Scalar divided by scalar will give you scalar. Scalar over scalar will give you scalar. Like I said, once you have this in mind that let vector be minus, let scalar be plus, all these principles will become 1 plus 1 for you. However, let me indicate this, please. Note, vector divided by vector does not exist. Does not exist. You cannot divide a vector by a vector. You cannot. You can add a vector to a vector. You can subtract a vector from another vector. You can multiply vectors. So you can add, you can subtract, you can multiply vectors. But you cannot divide a vector by a vector. You can't. You can only divide a vector by a scalar. So this principle, you want to take note of it. Please, let's move on. Let's move on. No time. Let us look at dimensions of vector. Dimensions of vectors. Dimensions of vectors. Dimensions of vectors. Dimensions of vectors. Vectors can exist in how many dimensions? Let us find out. There are 3 major dimensions that vectors can exist in. Vectors can exist in 1 dimension, 1D. So we can have 1D vectors, okay? Vectors in 1 dimension. Now, when you talk about vectors in 1 dimension, it is represented by a line. Represented by what? A line. And that line usually will have a starting point and an end point. The end point usually we use arrow there, where the arrow points to the direction. This is the starting point, and this is the direction. Are you following, right? This line you are seeing from here to here is the size. The line here represents the magnitude. The line represents what? The magnitude from here to here is the magnitude. Why the arrowhead represents the direction. The arrowhead represents what? The direction. Take note of that. The magnitude of the vector is the line, that line. So if I have this as point O, the starting point, and I have this as point A, the end point. So the length from here to here, OA, gives you the magnitude, the size, the value, the absolute length, the modulus of the vector. Why the arrowhead indicates direction. So as this arrowhead is pointing this way, it shows that the vector is going towards the east or the right hand side. The line could be something like this, means northward, north. The line could be something like this. It means west, west, that's left side. The line could be something like this. It means north, north, that is downward. So whenever you talk about one-dimensional vector, 1D vector is simply vector represented by a line. The line can be taken from our cardinal points. Then of course, the vector could also be inclined this way, where of course, if you look at this direction, it is northeast, northeast. The line could go this way, the line could go this way, which gives you northwest, northwest. The line could go this way, which gives you south. Okay, down is south, down is south, up is north. So this direction like this direction is southwest, southwest. And or the line could go this way, this direction, is southeast. Southeast. Okay? So all these are vector directions along a straight line. Such vector is known as one-dimensional vector. You can think of an ant. An ant. If an ant is walking on the branch of a tree, if an ant is walking on the branch of a tree, you notice that the ants usually move straight. Or whenever you see ants, you know, in convoy, they move along a straight line. And when they are coming back, they follow that same straight line. So you can use that to define vector in one dimension. See, the network is trying to interfere, so I had to boost. I had to boost the network a bit. I will be monitoring the network steadily. Okay, so once I notice the network is trying to disturb, I will go check the camera and boost the network. If I'm boosting it, you will be logged out. Don't leave. Stay tuned. Because once I'm done boosting, within just, a few seconds, if I restore the network back, you will be automatically logged in. Is that okay? The board is a bit blurred. The board is a bit blurred because of the network. So I'll still have to boost it. Please be patient. This is what we suffer. It's coming a bit clear, but let me boost. All right. So this will take me to the second dimension of vector. I think it's better now. Vectors can exist in two dimensions. So we have two-dimensional vectors. Two dimension, say 2D. Whenever a vector is said to exist in two dimensions, that vector is said to be in a plane. That vector is said to be what? In a plane. Generally, the vector is represented by xy. Now look at, if I have this cardinal point, say north, south, east, and west. Permit me to label north, south, east, west. Now imagine that this is the origin, the starting point. I could draw something like this to represent a vector, let's say OA. Now if you look at this vector OA, the vector is not along the vertical and it is not along the horizontal. So the vector is not north purely and it is not east purely. Remember, you can use y-axis and x-axis to represent this also. In fact, let me write it this way. Y-axis, that's positive y. This is negative y. Then this is, the east direction is positive x. The west direction is negative x. Okay, all right, the network is still okay, it's good. So this vector OA is not along the pure y-axis. It is not along the pure x-axis. It is between the y and x. If you're using the cardinal point, it is between northeast. Okay, so the vector could be here in this plane, southwest, the negative axis of y and x. It could be here in this plane, in this quadrant, okay, southeast. It could be here in this plane, in this quadrant, northwest. So anytime a vector is not purely vertical or it is not purely horizontal, rather it is inclined at an angle. This is the angle. Let me label this as theta. That vector is said to be in two dimensions. If you want to define that vector, there are two axes you use in defining it. Since the vector is between x and y axis, it means that that vector can be located using x and y coordinates, using x and y values. I hope you're following the class, right? So that is it. That is it. Like this vector OA now has a value in the y direction. It has a value in the x direction, since it is between x and y. Such vector is said to be a two-dimensional vector. Like I said, the vector is defined by two values. One is the x coordinate and the other one is the y coordinate. Is that clear? Vector in two dimensions. Vector in the plane. The network, I don't know. All right. I think it's still on. Let's see. Now, this will take us to the last dimension of a vector. Vector can be in three dimensions. So 3D. I don't have enough space here to show that anymore. But I just want you to know, whenever you hear that a vector is in three dimensions, that vector is in space. This is a vector in space. This is a vector in space. In space. It is defined by x, y, and z axis. It is defined by what? X, y, and z axis. On this channel, I have pre-recorded video lessons already that deals with that part. Are you following, right? Or that dealt with that part rather. But all the same, as we move on, we are still going to see how we handle vectors in three dimensions. At advanced level and further maths, we meet that. Are you getting me right? In physics, except when I move further ahead in this topic, in the advanced level form, that's when I will talk about vectors in three dimensions. For those that are in colleges, are you following, right? Yeah, in Nigeria here, we'll talk about secondary school. You don't deal with vectors in three dimensions in physics. Rather, you meet it in further maths. So for now, I will not go into details here. However, on this channel, I've got a pre-recorded video lesson on vectors that dealt with this part. All right. We are moving. We can now look at the algebra of vectors. The algebra of vectors. Okay? And to bring in the algebra of vectors, we will talk about resultant vector. Algebra of vectors. Algebra of vectors. Remember, like I said, this is a 1-hour class. If you have not subscribed to this channel yet, make sure you hit the subscription icon. So subscribe right now, okay? And turn on your notification bell. If you click on the notification bell after subscribing, click on the notification bell and then a menu will pop up. A menu will pop up. Click on all. So this is the whole idea. Subscribe, click on the notification bell, select all. The reason is whenever I upload any content, you will be notified. Or whenever I come on live like this, you'll be the first person to be notified, okay, that GMAT 41 is on now for you to join our classes. But like I said, we have a timetable that is stable now. I promised and I kept to it. I had told you friends that from September 1, we'll have a steady time that we'll be having our online classes. Monday, Wednesday, Fridays, 8 p.m. to 9:30. Are you following? 8 p.m. to 9 o'clock or 9:30. But sometimes network might interfere that I may not start immediately 8 p.m. I may be around trying to set up everything, but network may just interrupt. So you stay on once it is 8. Are you following, right? And you'll receive the notification once the class kicks off. Algebra of vectors. I'm going to wipe the whole board. I've shown you vectors in 2 dimensions, vectors in 1 dimension, and vectors in 3 dimensions. Look at vectors in 2 dimensions. To analyze it, we use Pythagoras rule. To solve problems of vectors in 2 dimensions, we use Pythagoras rule. Are you following, right? We can also use the concept of SOHCAHTOA. Can also use the concept of what? SOHCAHTOA. These are things you're meant to know, but don't worry, we are going to take them one after the other. So having stated vectors in the dimensions of vectors, remember I told you this one in 3 dimensions, we use x, y, and z axis to locate or define such vectors. Let's move on to algebra of vectors. Algebra of vectors. Calculations that are being done on vectors. Algebra of vectors. Algebra of vectors. Algebra of vectors. Okay, so like I said, vectors can be added, vectors can be subtracted, vectors can be multiplied. Are you following, right? Vectors can be added, subtracted, or multiplied. But you cannot divide a vector by a vector. I've actually shown you that here. A vector cannot be divided by another vector. That operation cannot be done. Is that okay? So I can give you problems where you can add 2 or more vectors. I can give you problems where you can subtract 2 or more vectors. I can give you problems where you can multiply 2 or more vectors. Before we move on fully into this algebra of vectors, I would like to have us define resultant of a vector. Resultant of vectors. Resultant of what? Vectors. We have to define it because whenever you're talking about algebra of vector, you're trying to solve questions, problems on vectors. You're trying to resolve problems, challenges on vectors. By the time you solve a problem on vector, your final result is called the resultant. So what is the resultant of a vector? Let us define it. I hope you're ready, right? The resultant of a vector. The resultant of a vector is simply a vector which can be represented in magnitude and in direction as 2 vectors, 2 or more vectors acting together. One vector that can be represented in magnitude and in direction as 2 or more vectors acting together. That is what the resultant of a vector is. So this resultant of a vector will produce the same effect in magnitude and in direction. Because like I said it is one vector that would have the same magnitude and direction as 2 or more vectors acting together. So any single vector that will produce the same effect in magnitude and in direction as 2 or more vectors acting together is what we call the resultant of a vector. Resultant of a vector is a single vector. Which would produce the same effect. In magnitude, which will produce the same effect in magnitude and direction. As 2 or more vectors acting together. So this is what the resultant of 2 or more vectors is. If I give you this to be a vector, this to be 2 vectors, and I give you this other one to be another vector. Okay, so we have these 3 vectors. If I ask you to find the resultant of this vector, it is going to be another single vector, which on its own will have the same effect in magnitude and in direction as these 3 vectors acting together. Is that clear? All right. Having defined what resultant of a vector is, when you come to vector algebra of vectors, by the time you add 2 vectors, the answer you get is called the resultant. That answer will have the same effect, will have the same magnitude and direction as the vectors you added. If you subtract 2 vectors, The answer you're going to get is called the result. Multiply vectors as well to the result you get will still have the same magnitude and direction as the two or more vectors that you multiplied. So having said this, let us move on to the algebra of vectors in one dimension. Let us get their resultant. Resultant of vectors in one dimension. After that, we'll look at resultant of vectors in two dimensions. Of course, when we talk about resultant of vectors in two dimensions, that is when we now bring in the laws of vectors. We will touch a bit of Pythagoras theorem. Of course, we use the soft questions. We'll talk about parallelogram law, although we don't have anything like Pythagoras law of vector. But I want to expose something to you, friends. To understand parallelogram law, it actually comes from Pythagoras rule. Because the truth of the matter is that even parallelogram law of vector and that cosine rule formula that we use in solving problems under parallelogram law of vector, it's actually an extension of Pythagoras rule. So I'm saying this now so that you try to work on Pythagoras rule. Once you understand Pythagoras rule, parallelogram law of vectors, and how to use the solve problems to become 1 plus 1 will become 1 plus 1. Then we'll now have triangular law of vector. That one is on its own. Usually triangular law of vector, applying it, you do it geometrically. You have to construct. I'm going to hold a special class on that because I would be needing my math sets, all right, pencil, ruler, and compass to be able to solve problems on triangular law of vector. Is that okay? Yes. For now, let us look at algebra of vectors in one dimension. Algebra of vectors in one dimension. So I'm going to wipe this. I've defined this term. Take note in case you are not able to copy your notes completely in the live class. At the end of this live class, a copy of this live class will be made available so that any other person can take it any time. You can come back, replay, and copy your notes. Even at that time, you can control me. Maybe if there is something I said you didn't understand at that point, you can pause, take me back, and replay. Listen to it. Okay? So, and that's one unique advantage of online learning. Let us look at algebra of vectors in one dimension. Let's see how we find the resultant. How can you get the resultant of vectors in one dimension? Algebra of vectors in one dimension. Good. Before we move on to this, I would like to state clearly that in handling algebra of vectors in one dimension, we can add and or subtract them. But generally, whenever you are dealing with vectors in one dimension, what you actually do there is addition. You add generally. Although we'll talk about subtraction, but that subtraction is actually obtained from addition process. The only thing is that for you to get subtraction in vector resolution, when they're in one dimension along a straight line, then one might be going this direction, the other one might be going the opposite direction, leading to your subtraction. But all in all, you are actually adding them. What you are doing is algebraic addition. So let me say this before we pick a question and then see how we handle that. Are you ready? You can write what I'm about to say. To obtain the resultant of vectors in one dimension. To obtain the resultant of vectors in one dimension, we simply take the algebraic sum of the vectors. Respecting their directions. I repeat. To obtain the resultant of vectors in one dimension, we simply take the algebraic sum of the vectors, respecting their directions. Now, this is one thing you want to know about vectors in one direction, in one dimension. If I'm giving you a question now, or an examiner is giving you a question, it is either they tell you that the vector, the quantity, are you following right, representing the vector is moving either east, that is east-west, like this. East-west is horizontal. I follow. Two, that the vectors, the quantity is moving up, down, that is north-south, along the y-axis. The problem of a vector moving along the horizontal and then at the same time moving along the vertical. And then that question is under one dimension. It's not done. Because for something to move horizontally and vertically, it means it has become two-dimensional vector rather. So what am I saying in essence? For one-dimensional vector, it is either the problem is dealing with a quantity, whereby this is moving up and down, or left, right. Up and down is north, south. Left, right is west and east, or east-west. Okay, and what you do is to take algebraic sum, like I said. Take what? Algebraic sum. Algebraic sum would have to respect the signs. I said that. It will have to respect what? The signs. Whenever you are dealing with vectors, you have to select what is called sign conventions. Sign conventions. And I'm going to tell you the one we are going to adopt on GMAETS 41. We are going to use what I refer to as standard sign conventions, respecting our graph. So before we solve any question, I want you to note the following sign conventions. Sign conventions will be used for resolving vectors in one dimension. Resolving vectors in one dimension. Resolving vectors in one dimension. Let me say 1D, in one dimension. So what are the rules? Okay, now I am going to move eastward. Eastward will be positive. So let me say east or right, because our right direction is taken to be east. Then we have negative. Negative will be west or positive x-axis. In fact, let me indicate here positive x. This one is negative. This is west, which is left. So anytime a particle is going the left direction, if it is describing a vector, we are going to assign it negative. So this is negative x-axis, negative x. Good. And then when we have this going up is going to be positive. It's going to be positive, which is, of course, positive, which is north, and that north is up. And that is actually positive y-axis. Then I am going to put this down this way, which is south, and that's going to be negative, south, which is down, and that is negative y-axis. Are you getting me right? This is positive x-axis. This is positive y-axis. This is negative y-axis. Okay, axis. Let me remove this so you don't think it's minus. And this is negative x-axis. So we are using our standard graphical, representation. Positive of y is pointing upward from the origin. Negative y pointing downward, which is south from the origin. Positive x pointing right from the origin, and then negative x pointing left from the origin. So whenever a vector is going to the right, we'll assign it positive. If it's going up, we'll assign it positive. If it's going left, we'll assign it negative. If it is coming down, we'll assign it negative. Our first question. We'll try to round off. The network is a bit down. I think it's raining right now here. Okay, and who knows? We don't usually trust our electricity company whenever there is rain, so here we don't. So let's be fast so that in case anything wants to happen, at least let's solve a question or two, as the case might be, or as the time might allow, or situation might allow, under one-dimensional vector. But whenever everything goes dark, the class will end automatically because there's nothing I can do. Become a channel member, support this channel, okay? We have monthly packages, platinum or diamond level. Can send GMAETS 41, super thanks. Below each of our video, you will see the thanks icon. If you click it, YouTube gives you the opportunity to support your creators. Whatever you send to GMAETS 41, I'll really, really appreciate. That can also help me to support this program. Are you following right? I wouldn't be over depending on our electricity company. So please, do well to support GMAETS 41. Become a channel member. That one's a monthly package. I'll send GMAETS 41 super thanks. So we have this question. First question, question 1. Question 1. A man walks 10 kilometers due east and then turned walking 25 kilometers due west. What is the resultant? What is the resultant and direction of the displacement, of his displacement, of his displacement? Good. So you see, what we are looking for here is the displacement of the man, not distance. If we had been asked to find the distance, what we'll just do is to add 10 plus 25 kilometers. If we're asked to find the distance covered by the man, we'll just add 10 plus 25 without respecting the signs. And that will give us 35 kilometers for distance, because distance is a scalar quantity. You just add them together without respecting sign. There is no direction for scalar. But here we are asked to find the displacement of the man. Displacement is a vector quantity. Therefore, direction is important. Solution. Now, what we are going to do before we take the algebraic addition is to identify the direction. Now, look at the man walks this way, 10 kilometers to the east. That will be positive. Positive 10 kilometers east. Are you following right? And then we are told that the man turned and then walked back west. You know that the line connecting east and west is a straight line. That is why the idea of one-dimensional vector came in here. Are you getting me right? East, west is along a straight line. Are you following? So this is a problem on one-dimensional vector. Now the man now turned and walked this way per se, 25 kilometers. Now we are using negative for it. Are you getting me? 25 kilometers west. Remember I told you that west direction we are going to select the convention, the sign, negative for it. So that 25 is going to give it negative. Now I want to find the resultant. We want to find what the resultant. Permit me to draw this thing a bit better still. I am not drawing to scale. I'm not drawing to scale. This is just analytical work. Are you following right? So we have something like this. 10 kilometers, 10 kilometers, 10 km east. So this is positive. Let me indicate it since we selected positive for east direction. And then the man now walks from here, from this position now, the man turned, walking along the straight line again. Don't mind me that I am drawing it down. The man maintained this line. Are you getting me? Just turned and then walked straight backward again. So you take note of that. 25 kilometers. This will be negative 25 kilometers because it's going west. Now what is going to be the resultant? First hand, I want you to know that the resultant will face the direction of west. The resultant will go west direction. Why would the resultant go west direction? Because the west, the magnitude towards the west, the displacement of the man towards the west, the magnitude is greater than that of east. The magnitude is what? Greater than that of east. That is why the resultant should be pointing or will be pointing to the greater magnitude. Take note of that. When two vectors are moving in opposite direction, the resultant usually take the direction of the greater magnitude. Now, this would be the resultant R, we don't know. So how do I get the resultant? Resultant will be equal to, you take the sum, algebraic sum of the two vectors. If I call this vector vector A, if I call this vector vector A, the direction A, and I call this one B, okay, this is going to be A. Is this so necessary? Okay, no problem. Let me call this vector A. Let me call this vector B now. So the resultant vector, you know, for vector, we usually put arrowhead on top. We usually put arrowhead on top, okay, something like this. So the resultant vector will now be equal to A plus B. Simply take the algebraic sum. When I want to substitute now, I will respect the signs. Remember that B is negative. B is what? Negative. So if I am fixing the value, the resultant will now be, what's the value of A? Positive 10 plus 10. Then plus, what's the value of B? In the opposite direction, negative 25. Negative 25. If you resolve this together, you are going to get 10 minus 25, which will give you minus 15 kilometers. Minus what? 15 kilometers. What is the implication of this negative? You see, it comes out automatically, naturally on its own. Since the final result gave us minus, it simply means that the vector, the man, is moving in the direction west. Because it is west direction, it is negative. So I will now come here and write minus 15 kilometers. If I do not put this minus here, if I do not put that minus, I would simply write 15 kilometer, then perhaps in bracket I'll write west, because you need to indicate the direction. You need to indicate the direction. If the final result were to be positive, it means that the man is now facing east for this question. But like I said, however, I think this is the classical interpretation of what calculation on vectors in one dimension is really all about. So you wouldn't have this problem of determining the direction of that thing. However, if you don't want to go by this approach, knowing that the two vectors are opposites, you can simply do 25 minus 10 directly. If you do 25 minus 10 directly without even bothering yourself, this positive, this negative, 25 minus 10 will still give you the same magnitude, 15 kilometers, right? Then it is now left for you, because the 15 you are going to get will be positive. It is now left for you to know that that 15 kilometer, the direction of that resultant will now be west. Because the west magnitude is greater than the east magnitude, like I explained. But I don't like all of those stress or whatever. I like the direction to come out naturally from the calculation. So I follow the standard approach of solving vector problems whenever you are resolving vectors in one dimension. Simply take the algebraic sum of the vectors, respecting their direction. So that at the end of everything, the sign you get to the final answer will help you to know the direction. So I can write this, or you can say 15 kilometers, 15 km west. I hope this does not cut off. 15 kilometer west without the minus. Without what? The minus. But with my diagram and the sign convention I selected like this, if I have minus 15 kilometer, I may not put west anymore. Okay? The examiner, the lecturer, the teacher, if the person really understands what vector resolution is all about, even if you just write minus 15 kilometer without putting the west, the person should know that the minus indicates direction. And since our west is what we assign negative here, it means that the man finally faced the west direction. We are done solving this question. We are done solving this question. Let us take question 2. Question 2. An ant walks 30 meter. Let me just reduce the value. An ant walks, let's say, 12 meters up of a tree, and then faces down, okay, walks, all right, and then faces down, walking 5 meter. First stop. Find the resultant displacement, or simply find the displacement of the ant. Displacement of the ant. Before solving this question once again, remember what we are looking for here is displacement, and displacement is a vector quantity. If the examiner had asked you find the distance walked by the ant, distance is scalar, so it does not respect direction. There is nothing like putting minus in anything there. In this case, the distance covered by the ant is 17 meters. Straightforward. 12 plus 5, you get 17 meters. You don't respect direction in the case of distance because distance is scalar. It was an example of scalar when I was giving you that. In this case, we are looking for displacement. Solution. So without wasting time, we must not draw the diagram. We mustn't. I have analyzed all of this for you. The ant moved upward. Up is not. Up is what? Not. So that will be positive. And then next, face down and walked some meters downward. Downward is south. Negative y-axis. So by convention, we'll say we are using negative. All right, which means this is going to be 12 meter. This movement. The displacement here will be 12 meter, and the displacement here will be minus 5 meter. So that if you now take the resultant displacement, you know what you're going to get. So let us go. Should I draw the diagram? Is it necessary? Okay. This one is 12. All right, 12 meter up, which is not positive. And then later, walk down. From that point, it followed this same straight line. It followed this same straight line down. But this time around, walked just 5 meters. These 5 meters will be negative because it's facing down, negative. So if I take this vector as vector A, and I take this one as vector B, then the resultant is the algebraic sum. In this case, the resultant, which one is the greater magnitude? I think this is positive. So the resultant will go in the direction of that greater one. Are you following, right? So I could just draw something if I want between to show it's going up. Okay, so let's move on. Resultant in this case is going to be A plus B, vector A plus vector B, which will now give us A is 12 meter plus open bracket V is minus 5. If you do that, the resultant is going to give you 12 minus this, which is 7. Okay, so the resultant of the displacement of the ant is 7 meter. This 7 is positive, you know that. And because it is positive, it means it is up. This one I'll answer. If you're not careful, if you don't understand the concept of vector, you may misunderstand it. Or someone may misinterpret it. This thing you are seeing, the direction will be up. Reason is because we assigned positive to up, although the ant now face down. But why can we actually claim that the direction is still up? Why can we claim that the direction is still up, not down, that it is still northward? Reason number one, because the final result we obtained is positive, the resultant. And then reason number two, let me show you clearly that this thing is actually positive. Watch. The ant supposedly started its motion from here because this is the beginning part covering 12 meter up. Now watch. When the ant now turned facing down, it walked only 5 meter down. So the ant is still within the upward direction. He's still within the distance of the up, or within the displacement of the upward. The ant is still within it. Look at, if I said from here to here is 5, it means that the ant would be somewhere here. So the ant is still within the range of the upward movement. Am I communicating? So because the ant is still within the range of the upward movement, that is why this will be positive. Showing that although the ant has faced down, its direction actually is still assigned up. The only time we can conclude that yes, the ant is now down per se is if it crosses this starting point, assuming that the downward movement was greater than 12. Let's say something like 13, 14, 15, 12 point something. It means it has crossed the starting point. Then, according to vector analysis, since it has crossed this starting point, it is no longer within the upward direction. Say maybe the thing is as long as it came somewhere here, which is observed from value given. If this thing were to be something like 13 now, you know that the ant would have been somewhere here. Somewhere here. Are you getting me right? Which will now mean that it has gone to the negative. We can now say the direction of the resultant is down. Okay? So you see, obtaining positive here simply shows that the direction is what? Up. This is good. Let's take our last question for our class today. Let's check what the time is. This is 1 hour 20 minutes. 1 hour 20 minutes. So we'll have just 10 minutes or less. Think we can round that off. Question number 3. We have solved questions where, displacement is in different directions. Left, right, that's east, west. Up, down, which is north, south. Let us look at question number 3. Remember we are dealing with vectors, algebra of vectors in one dimension. Two vectors, 20 Newton and 35 Newton are moving in the same direction. Find the magnitude and direction of the resultant vector. Find the magnitude and direction of the resultant vector. So we have two vectors. They are moving in the same what? Direction. We are asked to find the magnitude and the direction. So you see, this is a very simple problem. We can assume that the two vectors are moving maybe upward, or downward, or right ways, or left ways, right? That is, either both of them are going to the north, or both of them are going down to the south, or both of them are going to the east, or both of them are going to what? The west. The choice is yours. It doesn't concern anyone. Does that make sense, right? But one very important thing is for you to know that the two vectors are moving in the same direction. Let me assume that I have this to be 20 Newton. All right, let's say this is vector A equal to 20 Newton. And then the other one is also moving in the same direction. Okay, vector B, let's say this is equal to 35 Newton. Since they are moving in the same direction, I can use positive for them. Or I can use negative for both of them. The choice is mine. Are you following? The direction was not specified, so I decided the direction. But all I know is that both of them are moving in the same direction. Now, what is going to be the resultant? The resultant will be something drawn like this. You see, I've shown it between the two vectors. And of course, I'm just drawing this to show you a general idea. If you were to draw this to scale, the resultant of this one will be longer than any one of the two. Since both of them are moving in the same direction, when you add the magnitude of the vectors together, you are going to get a value that is greater than each of them. So that's the whole idea. All right, let us solve this. Resultant, we don't know. The resultant vector, we don't know. But it will be going in the same direction as both of them. So resultant is the algebraic sum of the two vectors, which is the same as we're getting the magnitude of that guy. So this is going to be A plus B. Our A is 20. Our B is 35. If you add this together, you're going to get 55 Newton. And the direction will be in the same direction as the two vectors. 55 Newton in the same direction. In the same direction as the two vectors. Since the two vectors are moving in the same direction, the resultant will also go in that same direction. Pay attention now. The physics practical is going to be based on equilibrium. Is it equilibrium? Oh no, sorry about that. It's going to be based on simple harmonic motion rather. The physics practical, simple harmonic motion. How do you carry out simple pendulum experiment? Okay, so you see how it's been done. Then the chemistry practical is going to be based on people that call themselves power holding company. Let me check the network situation. They've just restored the lights, okay? So I'm just trying to round off. The chemistry practical to volumetric analysis. That is introduction to titration. The network doesn't want me to conclude my information again, but anyway, I must conclude it. So for our practical classes tomorrow, physics practical and chemistry practical, okay, visit the community section of GMAETS for the One's channel. The network has refused. Please just visit the community section. Are you getting me? However you want to locate the community, the choice is yours. I've always been telling people about it, and you will see the links to the practical classes tomorrow. Like I said, physics practical will be based on simple pendulum, chemistry practical will be based on introduction to titration, volumetric analysis. Okay, so I am done, and I'll be seeing you next week in our live class on Monday, mathematics, that class. Okay, good night, and do have a wonderful night rest.